We have 3 talks, and the first talk is entitled The Exact Multi-User Security of Tweakable Key Alternating Ciphers with a Single Permutation. The authors are Yusuke Naito, Yu Sasaki, Takeshi Sugawara, and Yusuke will give the talk.
Thank you very much. Okay, so my name is Yusuke Naito. This is joint work with Yu Sasaki and Takeshi Sugawara. So this is summary of my talk. We consider the security of any round key alternating cipher or KSC. So R is the number of rounds, and we consider R is any. And key alternating cipher construct block cipher by iterating permutation and XOR with subkey. So key alternating cipher has R permutation code and R+1 subkey XOR operations. So regarding existing works, tight single security was given for key alternating cipher with a single random permutation. On the other hand, regarding the multi-user security, the tight security was given only for key alternating cipher with R random permutation and R+1 independent subkey. So we proved the tight multi-user security band of the key alternating cipher with a single permutation and R-wide independent subkeys. So this means that the number of independent random values in the subkey is reduced from the R+1 to R. So let's start by introducing a key alternating cipher. So this figure shows the R-round key alternating cipher. And the block size is n bits, and it uses R n bit permutation pi1 to pi r, and it has R+1 n bit subkeys K0 to Kr. So this single round of key alternating cipher is known as even master cipher, and R-round key alternating cipher is referred to as R-round iterated key even master cipher. And key alternating cipher describes the computational structure of block ciphers commonly used in the real world, such as AES and many other block ciphers. So the probable security of key alternating cipher is their theoretical foundation. And proving the tight security bound of key alternating cipher has been an important research challenge in symmetric key cryptography research. So we consider these research topics for key alternating cipher. The first topic is proving the tight security bound. This means that we prove the security bound matching the attack bound Rn over R+1 bits. So this means that the attack complexity is 2 to Rn over R+1. And second topic is proving the security of any round key alternating cipher. So security proof covers any round key, R is any. And the third topic is reducing the number of independent permutations. So and ideally a single permutation. So this means that these permutations are identical. And fourth topic is reducing the number of independent subkeys. And our last topic is proving the multi-user security of the key alternating cipher. So the security of key alternating cipher was initially evaluated in the sense of SPR security in the single-user setting. So this figure shows the singular security SPR security game, and the adversary interact with the real world and or ideal world, and adversary try to distinguish between these two worlds. And in the real world, adversary interact with a single instantiation of key alternating cipher and its underlying random permutation. So in this case, the underlying permutation is assumed to be random. And from the real world to ideal world, the key alternating cipher is replaced with the random permutation. So since even master's work, several works, these works prove the tight single-user security bound of key alternating cipher. And these first works increase the number of rounds with tight probable security. And the second works reduces the number of independent permutations. More specifically, this work considers the security of key alternate cipher with a single random permutation. And finally, these works reduces the number of independent subkeys. So compared with the work for the single-user security, there are not so many results for the multi-user security of key alternate cipher. So in the multi-user setting, adversary win by breaking any of the user of the key which better than represents the real-world attacks targeting a particular service rather than a particular user. So this is a multi-user security game, and the multi-user security considers instantiations of key alternate ciphers, where the each user key are independent. And from the real-world ideal world, key alternate ciphers are replaced with random permutations. So the multi-user adversary can obtain more information than the single-user adversary. So the multi-user security proof is more complex than the single security proof. So regarding the existing work for multi-user security, there are only two works. The first work was given by Moha and Lux. They proved the tight multi-user security of the single round key alternate cipher with a single subkey. And then the second work was given by Huang and Tessa. They proved the tight multi-user security bound of any round key alternate cipher, but their work considered only the key alternate cipher with the R independent permutations. So these permutations are all independent, and R plus 1 independent subkeys. So an open problem from their work, these works, is to prove the tight multi-user security bound of any round key alternate cipher with a single permutation, and the number of independent random value in the subkey is less than R plus 1. So this slide shows our result. So we prove the tight multi-user security bound of the key alternate cipher, any round key alternate cipher with a single random permutation and R-wise independent subkeys. So the number of random value in the subkey is reduced to R. And to prove the tight bound, we use these two techniques. The first one is patterning coefficient technique, and the second one is a new technique we present called update resampling method. So here I explain these techniques. So this slide shows coefficient technique. So in this technique, we consider a transcript that is some information that an adversary obtained by query to these workgroups. So transcript contains such as pairs of plain text and ciphertext, and the input-out pair of the underlying random permutations. So by using the coefficient technique, we can derive a security bound by these steps. So the first step is that we define the bad event on a transcript. Then the second step is that we split all possible transcripts into a bad transcript and good transcript. So the bad transcript defined so that one of the bad event occurs, and the good transcript is defined so that the other transcript. And using the bad and good transcript, we can obtain the security bound by summing of these two bounds. And the first bound is upper bound of the probability that one of the bad events occur in the real world. And the second bound is the lower bound of this ratio for good transcript. So this probability is a probability that sampling of the real world oracle satisfy all elements in the good transcript. And this probability, this is the probability that in the ideal world, sampling of these ideal world, Oracle satisfy all elements in good transcript. So the most difficult step in this evaluation is evaluating this real world probability for good transcript tightly. Because we need to count the number of solutions for the internal pairs for each plaintext and ciphertext. So the number of solutions drastically increase according to the number of rounds. So the evaluation is quite complex for large R. So counting the number of solutions is not a reasonable approach. So in order to avoid the complex step, we modify the security game so that these internal pairs V1, W1 to VR are introduced in the transcript. So that is the internal pairs for each plaintext and ciphertext pair are uniquely fixed. So we don't need to count the number of solutions of the internal values, and as a result, the evaluation for good transcripts becomes simpler. So since in the ideal world we consider random permutations, which are monistic permutation, so there is no internal value. So in order to introduce the internal pair values in the transcript, we define dummy keys and dummy internal pairs according to the key of time ciphers. So and then we reveal the keys and the internal pair to adversary. So by this modification, the keys and the internal pairs can be introduced in the transcript. So the remaining step is defining a sampling method of these dummy keys and dummy internal pairs in the ideal world. So we first consider naive sampling method, which called forward sampling. So in this step, we define the internal pair from the first round to the last round. And the sampling method success if all pairs are constant with respect to the random permutation. So this means that for each input or output, there is no distinct output or input. So in other words, the failure event is an inconsistent event that is the collision occur at the last round. So more specifically, the last round inputs collide with the other some input defined by previously defined. So since the key and ciphertext are independently defined from the output, so these outputs are distinct, but the inputs are the same. So this collision offers the failure event of the sampling method. So by the Basset analysis, the failure probability is Basset bound half of any bits. So this means that the naive sampling method ensures security up to only half Basset bound security. So this is not tight. So in order to improve this bound, we make use of the resampling method. This is a proof method for triple encryption. So in the resampling method, the impulse sampling is introduced in addition to the forward sampling. So if the forward sampling fails by this collision, the last round is redefined by inverse sampling. So if as the forward sampling, if no collision occurs in the inverse sampling, then all the internal value can be consistently defined. So the failure event of the inverse sampling is that similar to the forward sampling, the sampling result collide with some output defined previously, and so these values are independently defined. So this collision offers the inconsistent case. So as a result, the failure event of the resampling method is that collisions occur in both forward and inverse sampling. And that means the security from the two collisions is 2n over 3 bits. So the security bound is improved, but compared with the naive method, but this is not tight. So in order to obtain the tight multi-user security bound, we update the resampling method. So we update the inverse sampling like this. So if our collision occur in this part, in the inverse sampling, then the round defined by the first sampling is update and restart the resampling from the updated round. And this update are up to the first round. So the updated resampling method are the multiple collisions. So the probability of the multiple collision is improved to these bits. So as a result, the updated resampling method can consistently define the internal pair up to the tight bound. Okay, this is conclusion I talk. We consider the security of our-round key alternate cipher, and for existing work, the tight singular security was proven for key alternate cipher with a single random version, but for multi-user security, in the multi-user setting, the tight bound was given only for the key alternate cipher with the R random permutation and R plus 1 independent subkeys. So we prove the tight multi-user security of any round key alternate cipher with a single random permutation and with R1 independent subkeys. And to prove the tight multi-user security bound, we present the updated resampling method. And finally, our result can be applicable to the tweakable version of the key alternate cipher. Okay, that's all. Thank you very much.
Thank you. So are there any questions, either on the mic here or on the chat? Yes.
Thank you very much for the nice talk. Is there anything left, or that's it with this topic?
For this topic?
Yes.
I think so. That's all.
That's it?
Yeah.
Okay, thank you very much.
Thanks a lot for the talk. I mean, I'm kind of a newcomer to this area, so I liked your overview site with the different kinds of things you can research, the different directions, like small number of independent keys, same permutation, etc. One thing that I didn't see, and I was wondering whether there exists any research in this direction, is whether you can tone down the assumption of uniformly random public permutation.
Yeah. For your question is
the question is there any? Is it interesting to look at key alternating ciphers where the permutation is not uniformly random? Less than something less.
Yeah. So I'm not sure it is possible to the tight security bound using the non-uniform random permutation. So I'm not sure.
Okay, any other questions? If not, let's thank the speaker again. Okay, so the next talk is entitled Tight Security of TNT and Beyond Attacks, Proofs and Possibilities for the Cascaded LRW Paradigm. So the authors are Ashwin Jha, Mustafa Khairala, Mridul Nandi, and Abhishek Shah. And Mustafa will give the talk.
Thanks for the introduction. So we will be talking about a tweakable block cipher called TNT. Before we go into its details, I would like to present a quote from one of the first papers on tweakable block ciphers by Liskov, Revest, and Wagner. It captures what we want from a tweakable block cipher and also somewhat why the TNT will fail, as we will see later. Essentially, when we have a normal block cipher, we have like something like the right side here, where we have we change the key, we fix a permutation, and that's the only permutation we can use. And then what we actually want in modes is that even after we fix the key, we can change the permutation. So we have some public parameters, and these parameters allow us to choose different permutations. And even though like here the colors are close to each other, they are not supposed to be close, they are supposed to be independent of each other. So in the same paper, they introduced one of the early constructions, which is known as LRW1, which basically you have two block ciphers. In the original paper, it's the same permutation, but it could be also different permutations. That doesn't really matter. And you encrypt the plain text once, you add the tweak, which is also n bits, and then you get the ciphertext. This is very simple construction, and it's kind of efficient, but unfortunately it's not secure, at least for CCA, because there is like, with just 4 queries, we can cancel everything out because the permutations are accessible from both sides, and you just encrypt, you change the tweak and decrypt, and then you encrypt again and decrypt again, and the first plain text and the last plain text are the same. So in Eurocrypt 2020, Pao et al. Presented an extension of this construction, which is they call TNT, tweak and tweak. So basically we can see the first 2 calls here as LRW1, but then we add an extra one at the end, so we have 3 permutations. And in the original construction, there are 3 independent permutations, and we XOR the same tweak in both locations between all the permutations. And in the original paper, they gave a security proof with 2n/3 security, and then they had a follow-up work with different set of authors in Eurocrypt 2020, where they gave 3n/4 security and attack in the CBA model. And there was a different paper in 2023 where the authors presented a bound for R repetitions instead of 3. And they used compositional techniques, so their bounds may not be very tight. But they had birthday bound for the TNT case. Of course, again, like this is because of the compositional technique. So if we're looking at the security, 2n/3 should be the bound. And the authors of most of these papers, they conjectured that actually the security could be even more than 2n/3. So why did we start to study this construction? Is because it's very efficient beyond birthday-bound secure TBC, at least at the time when we started. And it used a proof technique called the chi-square method, which at the time was relatively new method, and it was used mostly for CBA schemes, not for CCA schemes. So that was an interesting thing to look at. And all the attacks known on TNT were using only CBA queries. So yeah, they are valid for CCA, but they don't use the power of CCA. So what we do in this work is actually we show that the original bound was wrong. So we show an attack on TNT with birthday bound security in the CCA model. We also reestablish the bound up to birthday bound. And we give a single key variant, so we don't need 3 permutations. And at the end, we will present a generalized version of TNT or the LRW paradigm, which covers, let's say, 4 rounds or more, and it also covers other types of similar constructions. So just to sum up the results, before the double line, these are the previous results in this area. And the relevant ones are the 3 LRW1, which is TNT, and 4 LRW1, which is 1 more round. And then at the bottom, these are our contributions. So we correct the bound for 3 LRW1, and actually the 4 LRW1 was found concurrently to our LRW+, so it's the same bound. And yeah, we also give the 1 key TNT where all the permutations are the same. In terms of AES-based constructions or instantiations, our attack is the best known distinguisher on TNT because all the previous attacks are way beyond 69. So our attack is birthday bound, but there is a constant term, so it goes up to 69. So the first observation that leads to our attack is a bit straightforward, but it was not clear, I guess, before, and it's also not clear once you see it how it does lead to attack. But the observation is that if we cascade 2 queries, forward query and backward query, with the same ciphertext, but we change the tweak, which is something we cannot do with block ciphers, but here we can do because we have another input to change. Then by3 does not contribute anything to the CCA security because it just cancels out. So if we say fix a difference, so all our forward queries will use certain set of tweaks, but then the subsequent backward query will use the previous tweak plus delta, and delta is fixed throughout the experiment. We end up with a new oracle that looks like this, and this oracle itself can be seen as a tweakable block cipher. So now, if we fix also the plain text, then if this was a secure tweakable block cipher, it should be also a BRF in T. So it takes T as input and should return a random output. And we can observe the properties of that output and decide whether it's actually a secure BRF or not. And if it's not a secure BRF, then TNT is not a secure TBC. So the distinguisher works based on this oracle. So this oracle is the O delta M. It's basically constructs this oracle and fixes a plain text and a set of tweaks, and then just asks this oracle to encrypt these tweaks with the fixed plain text and records the ciphertext it gets at the end, or the decrypted plain text, and then counts the number of collisions at the output. And it may not be clear at first why the number of collisions will change in this construction, but actually we can estimate the expected number of collisions in the BRF, which is straightforward, but also in this construction. And using the variance method, we can find the bound that shows that actually up around the birthday bound, we can see the difference between the two constructions. And all these parameters that we need in the variance method, we can estimate. We also have other types of analysis on ePrint based on statistics of random permutation or based on collision counting that show a different explanation of why this difference in the number of collisions occurs. But this bound is better than the other two methods because it also shows us not just that it's not secure beyond birthday bound, but it also scales, shows us when we can be confident that it's in the advantage, and it goes towards 1 as Q goes towards 2 to the n. So we also have experimental verification of these observations. So we implemented TNT for small block size with random permutations. And we count the ideal case, which is the PRF case, versus this type of constructions. And we see that the number of collisions always goes double the expected number from an ideal PRF. We also estimated the success rate. So if you look at this theorem, we were not very tight with the constant to simplify the calculations, but actually from the experiments, we can see that the advantage is even higher than the theoretical advantage, and the success rate goes to close to 1 just by a small factor compared to the birthday bound. We also implemented the collision counting using GIFT64, also a 64-bit instantiation of TNT, and we can find high success rate with about 72 hours of computation. Now, there was, as I said, security proof that contradicts this result. So we need to understand not just why this result happens, but why the proof was wrong. And the proof, as I said, used something called the chi-square method. It's quite an involved technique, so we don't have time today to go into the details, but just a small part of the method. Basically, there is a step where we have to estimate the distribution of the internal values of all the queries we have seen so far. And based on that, we estimate the distribution of the next value, or the internal values of the next queries. And the reason we have more collisions is because there are bad events that happen inside and bad collisions. One of these bad events is that we have first a forward query that calls by2 with a certain value, and then in the subsequent backward query, it calls by2 with a different value. And then what happens if we have another forward query that calls by2 with a value that appeared in a backward query, then the subsequent backward query will be completely determined because it will have to call by the red one, by 2 with the red value because of how we construct the differences. And in the proof, they didn't have such events, and they assumed that all the backward queries will have degrees of freedom that they can estimate, so there will be a variable that will be uniformly distributed. And if we put the correct values in their proof, the proof breaks apart and it leads to a constant advantage. On the constructive side, as I said, we re-establish the birthday bound, and we also give the single key variant. So if we replace all the permutation with a single permutation, we just get a constant drop. We also give something called LRW+, which is essentially a generalization of the LRW tweakable block ciphers, where we have LRW1 in the middle, but it's surrounded by universal hash functions and universal tweakable permutations. And we can show that this construction has 3n/4 security, depending on the security of the universal functions. And we can use it to instantiate a 4-round TNT or a 4-round LRW1, but we can also use it to instantiate other types of construction. So to conclude, we show that TNT is only tightly secure up to birthday bound, giving an attack. We also show that adding one more round leads to 3n/4 bit security, and we generalize this into the LRW+ framework. There are a lot of open questions in this area, so is 4 permutations optimal to get beyond birthday bound security? Because so far it seems so. Can we have a reduced key version of the 4-round one? So let's say we use 4-round but with a single key. And what is the exact security of the 4-round one? So we don't have a matching attack on our bound. Our attack requires a lot of tweaks. So if we limit the tweak space to, let's say, 1 byte or 16 bits, what's the security? And also the exact security of longer iterations, so more than 4 rounds. Thank you, and maybe take questions.
Thank you. Are there any questions? Okay, then I have a question. So the attack you showed shows that there was a problem in the original proof. Do you have a personal opinion on maybe how to make sure that all the proofs are correct, and what did you do yourself to make sure that your proof is correct?
I think the problem with this particular proof was that I think it didn't take the adaptive power of the CCA model into account. So, like, even when reading the proof, that's kind of how we started to find the problem, is that the attack made a lot of, the proof made a lot of assumptions that you can see they are not really taking the adaptive nature of the adversary into account. So I think maybe, like, in our proof, we use a different technique, so I think this problem is not there.
Okay.
Thank you.
Any other questions? If not, then let's thank the speaker again. Okay, so the last talk of this session is Post-Quantum Security of Tweakable Even-Mansur and Applications. The paper is by Gorian Alagik, Chen Bai, Jonathan Katz, Christian Mayens, and Patrick Struck. And Patrick will give the talk.
All right, yeah, thank you for the introduction. So yeah, let's dive into. So first, as the title suggests, we look into the Even-Mansur cipher. And this is a very simple construction of a block cipher from a public permutation. And how does it work? So the Even-Mansur cipher has 2 keys, K1, K2, of the same length as the block. And then what you do is you take your input X, you first XOR the first key, K1, you then apply this public permutation P. The result you XOR with the second key, K2, and the output Y will be the ciphertext. So throughout the talk, we'll make the following distinction. This construction as a whole is what I refer to as the construction, and this underlying P, this will be the primitive. And the other part you can see from the title is that we are interested in post-quantum security, and very roughly we have 2 different types of models we can consider here. First one, Q1, or also what is commonly known as post-quantum security, means we have a classical challenger and a quantum adversary. And the other one is Q2, or quantum security, we now also assume that our challenger, who represents the honest users, might also have quantum computing power. And throughout this work, we're only focusing on this Q1 model. This means particularly that the adversary is limited to local quantum computations. In the case of the Evan-Mansour cipher, this means you have classical access to the keyed construction, because these are the ones that are provided by the challenger, and the challenger only has classical computation power. And then there's quantum access to the public primitive for the adversary. So if you think of this permutation, as I said, it's public, so any quantum adversary could run it on a quantum computer and evaluate on a superposition of inputs. Now the positive thing is, like my 4 co-authors on that paper, they already showed the post-quantum security of the Evan-Mansour cipher 2 years ago at Eurocrypt. And so we built upon that. Now our goal for this work was to extend the results by showing post-quantum security of constructions which rely on the Evan-Mansour cipher. And in particular, we looked into 3 constructions. The first one is Elephant, which is an AEAD scheme, and was a finalist in the NIST competition on lightweight cryptography. The second one is Chesky, which is a message authentication code and an ISO standard. And the third one is Minalpha, which is also an AEAD scheme, and it was a round 2 candidate in the CESA competition. And for all of these, if you look into the proofs for these schemes, they always consist of 2 parts. Basically, the security of the underlying cipher they're using, and then the security of the mode. And it turns out the second part, the security of the mode, that then easily extends to the case of quantum adversaries. And the critical part when you switch to the post-quantum setting is the first step when you show security of the underlying cipher. All right, so as I said, the post-quantum security of the Evan-Mansour cipher was already shown by my co-authors. And essentially, so what they proved is the following, like the adversary distinguishing the real world here, where the quantum adversary gets classical construction queries to the Evan-Mansour cipher, and quantum primitive queries to the permutation P, is indistinguishable from the ideal world, where its classical construction is to some ideal cipher R, and quantum primitive queries to the underlying permutation P. All right. Looking at how they proved it, you can think of this as the adversary running in Q+1 stages, where here Q is now the number of construction queries by the adversary. So what does it mean? We have all the stages consist between the phases between 2 construction queries. So the adversary starts, can make a bunch of queries to the permutation, indicated by the P here. At the end of the stage, it basically makes 1 query to the cipher, and then the response is given to the next stage of the adversary, where it can again make arbitrary number of permutation queries, and so on and so forth. Right, so and then the general proof works by doing a hybrid sequence where we gradually replace the different invocations of the Evan-Mansour cipher by an ideal cipher, by this random permutation R. So if we look at the particular hybrid HI, means we've now replaced the first I invocations of the Evan-Mansour cipher by this ideal cipher. And the relevant part you can see here that at some point towards the end, we now have this P tilde. And this essentially is the same as P, with a bunch of points of the permutation are swapped. And these are some necessary modifications to ensure the consistency throughout the game. And this, like for larger I, this P tilde gets more and more messed up, so there are more and more points that got swapped. But also towards the end, once we proceed through all the hybrids, finally for I equal Q, this P tilde disappears. So you can argue with this is a bit like this proof by procrastination. So they postponed the problem of dealing with the P tilde until eventually we pushed it out of the whole hybrid sequence. All right, now to do these individual hybrid steps, in prior work they used 2 technical lemmas that they introduced. The first one is a resampling lemma for permutations, and the second one is a reprogramming lemma in terms of expected numbers of queries. So here we will only be interested in the first one. So let me quickly recap how that works. It's a 2-stage security game. So in the first phase, you have a distinguisher D0, which gets quantum access to some permutation P, can make a bunch of queries to it. And at the end, it outputs some quantum state for the second stage of the adversary. After making the output, a random bit B is chosen, and 2 random points S0 and S1 are generated. Then the game sets up 2 oracles. The first one, P0, is just the same P as before. And P1 is also P, except now for these 2 random points, it will swap these 2. In the second phase of the game, the adversary then gets the state of the first after the first phase and these 2 random points. And it then gets access either to P0 or to P1 and has then tell apart which was the case here. Okay, and then for this they provide a concrete bound. Now if we look again to the security of the Evan-Mansour cipher, now each of these hybrid steps from switching from HI-1 to HI consists of 2 steps. The first one replaces the particular query to the Evan-Mansour cipher by the ideal cipher R, and then it fixes P by replacing it with this P tilde, which has a bunch of swapped points here. And all the remaining construction queries for the Evan-Mansour cipher, they still rely on this normal, the not modified permutation P. And for this step, it's essentially applying this resampling lemma, and then afterwards there are some bad events to deal with. And the second step is then, after making this change to R, in the next phase, this P tilde gets replaced by P, and this one uses the reprogramming lemma, which I did not show you yet. All right. As I said, our goal was now to extend these results to other schemes, and one example I mentioned was Elephant, which you can see here. And now there are 2 problems of just applying the prior work here. First one is for Elephant, they basically rely here on what we call the tweakable Evan-Mansour cipher and not the plain Evan-Mansour cipher. And the second one is that for Elephant, they use some key expansion, which you can essentially see here, like the keys get with this mask term. You have a shorter key, which you first pad with zeros up to the block length, then apply the permutation and then some other functions. But the key is not of the size as the block length. All right, let's formally go into the tweakable Evan-Mansour cipher. So it looks very similar. The only difference now is when we have 1 key, and instead of XORing this key, we have these tweak functions F1 and F2, which now take some value T, which is the tweak. And then this tweaked key is the one that is XORed to the message. And the other one is the tweakable Evan-Mansour with key expansion. And for this, we consider the case here where now this tweak function expands the key, what we have seen on the previous slide for Elephant. Okay, now to show the post-quantum security of the constructions, we essentially need here Q1 security of the tweakable Evan-Mansour cipher. That would be sufficient to show security for Chesky, because it does not have the key expansion thing. And we need this Q1 security of this tweakable Evan-Mansour cipher with key expansion to show security of Elephant and for a variant of Min-alpha. All right, then our main result essentially gives us that we can show post-quantum security of the tweakable Evan-Mansour cipher with the key expansion, with this particular bound, which I don't want to go into. And there are some details regarding this function F1 and F2 I'm not mentioning right now. And then the other part, like once we have this result, we can easily get the post-quantum security of the tweakable Evan-Mansour cipher without the key expansion. And yeah, once we have these established, then we can already use them for the security of Elephant, Chesky, and Min-alpha. All right, our proof is inspired and closely follows the prior proof for the plain Evan-Mansour cipher. So we also consider this hybrid sequence of Q plus 1 hybrids, where we gradually change the different construction oracles. Now, when you look at this here right now, it's only I replaced this Evan-Mansour cipher with the tweakable Evan-Mansour cipher here. Now remember I said for the prior proof there were 2 steps using the resampling lemma, bad events, and this reprogramming lemma. Turned out the second step, we can use the same reprogramming lemma that was there, and everything works out fine. But for the first step, the prior work does not work. We cannot apply the same as before. In particular, there are 2 problems here. The first one is, I mentioned there are these bad events, there were 3. And one particular bad event, we could simply not bound, or we cannot bound for the tweakable Evan-Mansour cipher. And this turned out this is fundamental problem for the tweakable Evan-Mansour cipher to get the post-quantum security. Hence, it affects also all three elephant, chess key, and min alpha. The second problem is the resampling lemma from prior work that could not handle the key expansion. And, well, as I said, only elephant and min alpha were using this key expansion, so this problem is only relevant for these two schemes, but not a problem for chess key. All right, let's look in how we solve it. So for the first problem, that was the problem with the bad events. Turns out actually this solution is very simple. So it said this prior work had this proof by procrastination, so they postponed the problem until it disappeared. Actually, turned out we just need to postpone it even more. What do I mean by this? Well, I said we have this messed up permutation p tilde here, but we always, in the prior proof, it used the not messed up p permutation still for the construction queries. So we're not doing that change, so we still keep also for the tweakable Evan-Mansour construction here, we also use this messed up permutation. This means it's now not just the permutation that gets more and more messed up as we proceed through the hybrids, but also the construction oracle gets also more and more messed up. But in the end, we also push it out of the hybrids eventually, and by that change, we do not get into the problem of this bad event, which we could not bound for the tweakable Evan-Mansour cipher. And also turns out that this change you could also do for the plain Evan-Mansour cipher, so by also using this messed up p tilde for this construction. But this doesn't change the overall result there. All right, the second problem, that was the resampling lemma. So as I said, in prior work, there was this resampling lemma for uniformly random points. What do I mean by this? Basically here, S0 and S1 gets chosen uniformly at random after the adversary could make a bunch of queries in the first phase to the permutation P. And now for our case, we now give a generalized version of this resampling lemma, which allows for more general distribution of the point S0. It also allows the distribution of this point to be chosen by D1 after the first phase, so like after making a bunch of queries. At the end, D0 can specify what's the distribution, how S0 needs to be chosen. And even more general part, like for the first one, like this distribution of S0, that may also make a query to P. And if you remember from the prior slide with the elephant construction, that's the relevant part where we had like the key expansion also used the permutation P, and this is why we need this step that the point that it gets swapped are also involve a query to P. Now for this we can give some upper bound of the advantage, which is here in terms of the number of queries Q, some term epsilon, which gives you the maximum probability of any point S0 according to the distribution that the distinguisher was chosen, and then F, which was the size of the set from which the queries are happening. All right, to conclude, so we showed the post-quantum security of the tweakable Evan-Mansour cipher with key expansion. And then we used this result to show post-quantum security of several schemes. So we had Elephant, which was the AEAD scheme and NIST finalist, Chesskey, the message authentication code and ISO standard, and this variant of min alpha, which also an AEAD scheme from the CISA competition. And as a technical contribution, we give this generalized version of the resampling lemma for random permutations, building on this prior work. And with this, thank you very much for your attention, and I'm happy to take questions.
Okay, thank you. Are there any questions?
Since we had a question earlier in this session about like avoiding errors and proofs and such, my memory is at some point y'all had one of those and posted about it on ePrint and clearly fixed it. Did you have any takeaways from that process?
Be careful with the proofs. So maybe for the rest, like at some point, like we did the post-quantum security Evan-Mansour cipher, and the problem we had at some point, we looked into the security of the FX construction, where it's not like the underlying permutation or the public permutation, but a keyed permutation. And well, the problem mainly for that construction was working with the bad events. We had some error there that basically the bound didn't give you the advantage you want to have from the FX construction. Well, you would, for the FX construction, the additional key of length m, and you would want the bound to also increase with that m, and basically we did not get this due to these bad events. That was a mistake in the final step of the proof at the end there, and yeah, it was overlooked. But I get your point from your talk that this is hard to be very sure about this.
Okay, any other questions? Okay, if not, let's thank Patrick and all the speakers of the session again.